All right, and we are recording. So today we're moving off of the arrow pushing, and we're just going to cover a little mini review of thermodynamics and kinetics, because it's going to become really important in future chapters when we're discussing reaction rationales, that we have a few of these things freshened up. So some of these things are tools I've been using a little bit and we're going to elaborate on and get a little bit more in depth also. So we're going to start out with reaction coordinate diagrams. And this is the classic y-axis is increasing energy, and then along the x-axis you have reaction progress. And what everyone's probably most comfortable with in this is that notion that we start out with the reactant, and then we have some kind of barrier to activation. And then once we go through the barrier of activation for a favorable process, we go from reaction or reactants to products. And this is something that everyone's seen before a bunch of times. I know I've referred to it a couple times already this semester. And what we're going to kind of talk through is, what does this look like in terms of a mechanism? What points of a mechanism correspond to these different points in a reaction coordinate diagram? So let's say we're doing some reaction where we have reactants, let's see here. We have something like this where we have some compound which has a component A and B bound to each other, and then we have reactant C. And in this reaction, we're going to say C is going to come in and attack B, breaking this bond, pushing the electrons to A. And this is just in general. What we're going to see as this happens is we're going to get that attack of the electrons on B, so we're getting our nucleophilic attack, and this is going to form a bond, or start forming a bond. And as this bond starts to form, that's going to exceed the allowable number of electrons around B, which is going to cause this bond to break, pushing the electrons to A. This happens in a concerted fashion where both C and the bond forming between C and B happens, and the bond breaking between B and A happens simultaneously. So oftentimes you see something drawn where you have an intermediate or high energy transition state that looks like this. And so this point up here is called transition state, where we have these bonds forming and breaking simultaneously. And then over in product, if I was going to redraw this, we could have A plus B to C as our product. So what's the difference between a transition state and an intermediate? Let's just go ahead and get this out of the way now. So this is a transition state. What's a transition versus intermediate? You probably use these terms interchangeably in the past, but they're not really interchangeable. They have very different meanings.
Intermediate has actual bonds in a reaction. It's in the middle of a reaction.
Mm-hmm.
And you can actually separate them.
They're observable. It's probably, yeah. So you're really close. So a transition state is, transition states are higher energy systems, and they're very transient. They're so transient, in fact, that you don't have stable bonds formed, and they're not observable. Whereas an intermediate is a high energy product which then undergoes rapid subsequent reaction, but it does have actual bonds formed. It's just a higher energy intermediate product. So transition states are going to be higher in energy than intermediates, and we're going to do some examples of intermediates. An example of an intermediate would be when we were pushing electrons in the last class, and we had, let's see, and we had this nucleophilic attack where the alkene attacked the proton, kicking off the bromide, and that gave us this is an intermediate.
I think we're missing. Are we missing?
That's an intermediate. Where the bromine would come in and do the subsequent attack on the positive charge as our second attack in the mechanism. So, because this hydrogen is now bound here, so it's CH2, these electrons that were being shared, one is now contributing to this new bond, but this one is missing.
I just
that
think we're
electron.
missing a C for some reason.
CH. Yeah,
There we go.
we are missing a C.
I feel better now.
Okay. So, on its way to doing this, however, and having this intermediate, we have this transition state where we have a bond breaking, a bond forming, and a bond breaking simultaneously. So you can see that because we don't have actual bonds formed or broken, they're in elongated states, they're not full bonds, and that's why we're going to have this higher energy transition. Even though this is high energy, we have a carbocation. This is stable enough to be considered an intermediate. Talk about that later. Do that. Any questions about this before we move along? Pretty comfortable? Did everybody get the email announcement about availability of peer learning assistants this week? All right. Utilize them, please. So, for a number of reasons. One, because they're an incredibly valuable resource, and that's 6 hours a week of available time for the 321 specific ones I've announced. There's also, we'll see how it plays out. We'll see what the usage is like. It's possible that if the 105 PLAs are not being utilized to full capacity, that we can make some of their time available in addition for 321 also, if the 6 hours are being really well utilized. So that's all, like I said, depending on how active the 105 groups, because we have 180 plus another 7, about 250 students in 105 right now, and divided by two people. But we'll see if they utilize the resource or not. So if we find, and what we found historically when we're doing variations on this, when students get together as study groups and make use of a tutor, or in this case a PLA, the people that are doing those study groups typically do better. Not only do they do better versus the average for the group, they do better than they were doing before they started that habit, which is more indicative of a reason for it working than the possibility of good students self-selecting to do more studying. But I just highly recommend doing it on a schedule, trying to find people that you can go do it with and work on problems. They're going to be able to help kind of coach through the concepts associated with the homeworks, and they can also They're going to have a whole bunch of possible problems available that they can run independently of the homework platform as well. So, or just help talk through rationale or maybe do explanations from a different perspective. So that's my pitch. Let's see here. Thermodynamics. This is new and it's terrible. Maybe it's just bored. So thermodynamics and kinetics are technically different things. Thermodynamics is really just a study of how much product is formed. And kinetics is a study of how fast it's formed. So, really good example would be rust, iron rusting in a slightly humid environment. Thermodynamically favorable, spontaneous reaction, which will occur because its product is lower in energy than its reactant, but it happens very slowly unless, even for a chemical reaction, you could consider it slow even if it's under ideal conditions where you have a humid, warm environment with salt in the air. Still going to be a pretty slow reaction. So we have to keep these things separate in our arguments because down the road we're going to be asking, is a reaction controlled via thermodynamic control or kinetic control? This is going to become something we're going to have to keep separate, especially in OChem 2. So let's jump into thermodynamics here and just talk about just basics of thermodynamics. So for any general reaction where you have A equivalence of reactant A, B equivalence of reactant B, and equilibrium, I always want to do that. C equivalence of product C plus D equivalence of products D, we can discuss what's happening in this reaction in terms of the ratio of reactants to products. So the equilibrium expression for this is going to be the concentration of C raised to the small c power, concentration of D to the D power, over A to A and B to B. And what this really is just the ratio, an adjusted ratio, for molar equivalence of products over reactants. So if we have a large equilibrium constant, what that means is that we've got a reaction that favors products. If we have a very small equilibrium constant, we have a reaction that's favoring the reactants, meaning it's biased this direction. Even though it's proceeding a little bit, it's favoring the reactant side of the equation. So, let's see here. This is related to Gibbs free energy. So, if we're looking at Gibbs free energy under standard state, or changing Gibbs free energy, this is going to be the free energy of products minus the free energy of reactants. So what's delta typically? Change. Change is always in science what minus what? Final minus initial. So this continues that trend because products are what we end with. It's the final state minus the reactants, which are our initial state. So the rationale carries through on this too. So you don't have to necessarily memorize this. You should always be able to go, oh, final initial, reactants minus products. Okay. So when we're evaluating change in free energy, we have a scenario where we have a reactant going through an intermediate or transition state, energy transition state, to product. And in this particular case, the delta between reactants and products is going to be our change in free energy for the reaction. So the greater the change in free energy, so I'm going to actually just see where you guys are real fast. Is this positive or negative change? Negative change. Because it's products minus reactants. Products are a smaller value, therefore that's negative. So negative Gibbs free energy change is favorable, or also known as spontaneous. What if we have something like this? Now we've got a product which is higher energy than the reactant. This results in a positive delta G for this reaction and is typically described as not favorable or non-spontaneous. Now, what we see in terms of spontaneity is that we have equations which, are we going to go into it? Yeah. Which relate these two. So those are constants. We've got the ideal gas law. We've got temperature in Kelvin. So really, those two variables are directly related via constants. So when we're evaluating whether or not something is spontaneous or non-spontaneous, favorable or not favorable, what does that mean in terms of equilibrium? Well, if something is favorable, it means it's going to bias towards products. If it's non-favorable, it's going to bias towards reactants. But something being spontaneous or not spontaneous doesn't mean that we aren't getting some product formed. There's still an equilibrium system that's established. It's just that it's favoring the reactant side of the equation. You had a question back here?
Yeah, if the temperature is one of the variables, doesn't that mean that delta G is no longer under standard conditions? So wouldn't it be delta G, not delta G not in that formula?
And that's an adjustment based on the relationship from the standard state. And the reason is because as we change the energy level that's available, it's going to change the energy level of the reactant, but not the energy. Well, we'll get there. We'll get there in a second. So there's, let's see here. Let's do a proof of concept of this really fast. So let's say, this is an example from the book, which is a good example. Let's say that we actually want to look at the change in Gibbs free energy for the conversion. It's this everyone's new favorite thing in the whole world, from an axial. Everyone's like, oh no, it's still here. See, fluorocyclohexane. Bless you. To the equatorial form at 25 degrees Celsius is negative 0.25 kilocalories per mole. This is a little odd because we're using kilocalories instead of joules, so we're using a different value for R than what you guys are probably accustomed to. Instead of using the 8.31, we're going to use 1.986 kilocalories per mole Kelvin, but it's just a change to the R term. And the question is here, what's the percent of the reactants to products, or products to reactants at equilibrium? So we had this discussion where, like, oh, okay, so we've got this fluorocyclohexane, so it can be either in the axial position or it can ring flip. Stays on top, but now it's in the equatorial position. And so the question is at equilibrium, what ratio is in this form versus this form? Now, which form should be preferred? Equatorial. Too many U's. So this should be preferred, but only slightly because fluorines are actually quite small. So the degree of 1,3-diaxial interaction is pretty limited. But we should be slightly favoring the equatorial conformer. So based on this, we can jump into this equation and say, well, if that's the change in energy for this process, and delta G equals negative RT, natural log of equilibrium expression, and we want to break out natural log KEQ, delta G minus RT. So we've got negative 0.25 kilocalories per mole over negative 1.986 times 10 to the negative third kilocals per mole Kelvin. That's our expression, 298 Kelvin at 25 degrees Celsius. So let's see here. Kelvins will cancel, moles will cancel, kilocalories cancel. Everything should cancel because equilibrium expression is unitless. And this gives us a KEQ, once we get rid of the natural log, sorry, skipping a step here, of 1.53. Now, how does this get us a percent product to percent reactant?
Well,
Divide 1.53 by 2.53.
Yes, why?
Because for every one molecule of reacting, you have 1.53 molecules of products, so you add them together and then just divide by its product.
And for those of you who don't know what he just said, remember that KEQ not only equals delta G, it equals basically your concentration of your product over concentration of your reactant. In this case, that's what we're looking at. So if this equals 1.53, what that means is that you have a ratio of 1.53 to 1 for your product to reactant. And the reason it has to be 2.53 to find the percent is because if it's a ratio of 1.53 to 1, that means that there is one part that is 1.53, and there's another part that has a full part allocated to it. So the total number of parts is 2.53 parts in the system. So this is 1, so this is 1.53. If you add them together, that's why 2.53 for the whole. So the ratio of product, percent of product, is 1.53 divided by 2.53 times 100, and I think this is about 60%. So you can see that we're just slightly favoring the product. It's a 60% to 40% relationship in this case because the degree of 1,3 diaxial interaction is pretty small. Now, why do we go through all this? Hopefully to reinforce that equilibrium is just an expression of products over reactants, and that we can get to that expression by looking at Gibbs free energy, or we can determine Gibbs free energy by experimentally looking at ratios of reactants and products in equilibrium, and therefore relate it to or find Gibbs free energy. Other thermodynamic terms that we need. Any questions actually before I move along? Yes.
We wouldn't have a math question like this on the exam, would we? Where we need to pull out our calculator.
We do in Biochem 1. That's right. I don't allow calculators. Oh, I would have to allow a calculator if I did this. Tempted now. Tempted. Super tempted. I don't know. Haven't written the test yet. Probably not. I'm going to make you guys are going to be pushing so many electrons. Probably won't have time to do this.
Okay.
But it would be totally reasonable if you had a calculator. Okay, so here's a question. Enthalpy. What does that typically correspond to in terms of chemistry? Heat, right? Typically corresponds to heat. There's conditions in which it doesn't, but they usually involve large changes to volume or pressure, and under normal chemical reactions, it's fairly unusual. So we usually lean on this is a pretty robust relationship. You can usually just think of enthalpy as heat. And one way I like to get to this is to look at, because it's a delta, heat required to break bonds minus the heat released from forming bonds. And this almost always is a curveball for people. Because when you think of a chemical reaction, you're usually thinking of a favorable reaction involving a decrease in energy, or releasing energy, because this would be exothermic. And when you think of an exothermic reaction, you're thinking of you're making some bonds and you're releasing energy. Is that usually how people process this? Like, am I off track in terms of rationale? No? I'm not off track, or it's somebody like that done. I never think of this. Why would you make this assumption that this is what I spend my time thinking about? Does it seem odd to anybody that I made the statement, heat released from forming bonds? Heat required to break bonds.
Usually considered the opposite way.
Right? Typically, because we spend so much time talking about exothermic reactions that are spontaneous releasing energy. They are largely in part to the enthalpy being favorable, negative, because more energy is released from forming the bonds than is required to break the old bonds. Anytime you break a bond between two things, you have to put energy into breaking that bond. Energy is required to go to that bond to break it. It will require heat to break a bond. Anytime you want to form a bond, . 'Cause formation of that bond will release energy, because the fact that it formed means you went from a less stable system to a more stable system. Forming bonds releases heat. So what makes a reaction favorable in terms of enthalpy versus not is more heat released than required for the whole system. A good example of this. And this is one of those multiple choice kind of tricky questions. Really, if this bond is broken, how much heat is absorbed, heat is released? Not enough information to know. Most people will pick not enough information to know because they're expecting some kind of big equation. But anytime you break a bond, it takes energy to break that bond specifically. If there's a question about how much energy does it, is it positive, negative, or not enough to know to form this bond, you know that it's going to have to release heat to form the bond. So, let's see here. Since we're on this rationale, okay. If we were to assess this particular reaction, to go from this reactant to this product, we need to break this bond and this bond, and we need to form this bond and this bond. Yeah. So whether or not this reaction is thermodynamically favorable in terms of enthalpy, change in enthalpy, is more heat required to break these bonds than is released by forming these bonds? Or conversely, is more heat released by forming these bonds than is required to break those bonds? Which would make it favorable in terms of going towards products. And in this particular case, we can look up all of these bond energies, and we can find that the pi bond for ethane is 62 kilocalories per mole. The bond between the hydrogen and the bromine is 88. So we got 150 kilocalories there per mole. And then on this other side, we've got a carbon-hydrogen bond, which is 101 kilocalories per mole, and we've got carbon to bromine bond, which is 71, so we get 172 kilocalories per mole. So we are releasing more heat than is required, so this is going to be thermodynamically favorable in terms of the enthalpy term. There's a table 5.1 in your book has a summary of a lot of these common bond energies associated with changes in enthalpy. Any questions before we move on to the next thing? Okay. So we talked about the difference between thermodynamics and kinetics. Kinetics is speed, thermodynamics is how much product is formed independently of speed. So let's look at these differences. Under standard conditions, this is delta G naught, difference between our reactant and product. The difference between our reactant and our transition state is a different term that people have seen. It's got those two little plus signs next to it. Totally different terms. Now, it turns out this is the term we use for thermodynamics. This is the term we typically use for kinetics. Because the delta between where you start and the level that you need to get through this transition state is largely what's going to determine how fast a reaction can proceed. A really good example would be the hydrolysis of ATP to ADP plus inorganic phosphate, also plus energy, right? So this is energetically favorable process. However, the energetic barrier to this happening is so enormous that under normal biological conditions, you can have ATP basically considered favorably stable because it's such a slow reaction that it doesn't happen in any reasonable time frame for it to be relevant for biochemistry. Even though thermodynamically it's favorable, the barrier is so unfavorable it doesn't proceed on reasonable terms. So this value is incredibly important in terms of managing a reaction rate. And the way we typically do it in a laboratory is we increase the temperature. So if we increase the temperature, we can increase the amount of available energy for the reactant. And this could, without changing the requirements to reach the transition state, and we end up not changing the ratio of products to reactants, but we can change how they get there. Yeah?
So the larger the delta G dagger, the slower the reaction?
Yes. Yeah. So it's, let me just redraw this so it's more apparent. If you have a very high energetic barrier versus a medium or low energetic barrier to get through, let me see here. I think we have, yeah, this is a good time to talk about it. You have 3 requirements for a chemical reaction to take place. You've got to have, to improve the number of reactions taking place, you need to have a number of collisions. So if to form a bond, you have to have a collision, which means you have to have some kind of probability of 2 things colliding. So you can increase concentrations to do that, or you can excite those things that are already present with more energy. You need to have a fraction of collisions with sufficient energy to drive the reaction. So it's kind of like, it's probably bad to use vehicular accidents when we're this close to our first snow. So I'm not going to use that because last winter, first snow, I got T-boned at 30 miles an hour. Yeah, that was awesome. And that person had plenty of energy to wreck my truck. More importantly, if you have a soft collision because you don't have a lot of energy in the system and there isn't a lot of excitement and a lot of motion and vibrational energy, then they can collide, but then nothing happens. And then lastly, you need to have a certain fraction with proper orientation. And what heat really does is increases these two. When you heat a system, you're increasing the number of collisions and you're increasing the velocity of these particles as they collide with one another, so that you have a higher, and that extra energy gets you over this hump sometimes. Whereas something which has a very low energy is going of activation to overcome. If your energy of your system's up here, everything's just going to go right through it really fast. It's not going to take a lot of probability to get over the top of that. It's going to happen a lot more quickly. It's not going to change really the ratio, because the ratio for equilibrium is just the concentration of reactants over products. So it's not going to affect this, it's just going to affect how fast it gets there.
So equilibrium isn't dependent on temperature?
Is it? Or is rate dependent on temperature? Equilibrium doesn't affect anything associated with Le Chatelier's principles.
Okay.
Right? They're different. It's just that you can separate them in terms of, right? So if you want to drive a reaction to completion and we put heat on it, it's not because that makes the reaction possible. If we give a reaction heat, it's just going to proceed to products more quickly. But that same amount of heat is available for the reverse reaction to proceed too, because you have competing forward and backward reactions. It's just they're going to be going faster. They're still going to reach that same equilibrium.
So you're talking about another thing that is going to be mechanically favorable and thermodynamically favorable, where we have it's favorable because the delta G boundary is negative, delta G naught's negative, and then it's also the less high it goes above that line, the more kinetically favorable it is then, or
so the smaller
delta G dagger.
Right. So in terms of yes, in terms of increasing, I don't want to say necessarily favorable or non-favorable. It is favorable. It's more favorable if you have a lower energetic barrier to proceed. I'm going to follow up on this. I'll come back to you in just a second. Now, we've been talking about heat. The way enzymes work or catalysts work is by reducing directly intervening with that barrier and reducing it. And the way they do that is not through improving the number of collisions or the fraction, but dealing with orientation. So that it takes two things, physically orients them perfectly in the correct proximity. So, well, I guess it could be considered this also because of sufficient energy, and causes a reaction through a concerted mechanism that requires lower energy to overcome. So there's two, but also enzymes just increase rate of reaction. They don't shift your equilibrium.
Isn't delta G, delta plus, just another term for activation energy?
It is the activation energy. It's the energy required to, now, and here's the thing, is in like say a slow reaction like ATP going to ADP plus in organic phosphate. Every now and then, even with fairly low energy available, the stars align and one will make it up here and then it has the option of either going back downhill to this side or to this side. And when it chooses this side, it ends up in a more stable place, which has an even higher energy because the reverse reaction must go through that much energy change to go back reversibly. So you do have the ability, even with lower energy available, to very slowly proceed towards a product. It's just much slower than if you put extra heat into the system so that you can overcome this threshold, or have a catalyst which reduces the activation energy so that existing levels of heat can drive it over that moderate to small hump. So the last thing I wanted to throw at you guys for this chapter, and then it's a day, it'll be a relatively short lecture, is what one of these reaction coordinate diagrams looks like for the reaction we've been doing with alkenes. So if we have a reaction where we have a double bond in the presence of hydrobromic acid, the double bond does nucleophilic attack proton. This exceeds the number of bonds possible to the hydrogen. So we push electrons to the bromine. It's a pretty good leaving group. We've got our reactant. We've got this going to an intermediate. We've got a reactant. Got an intermediate, and the intermediate has its first transition state, which occurs as this bond breaks, this bond forms, and this bond breaks. So this orange state corresponds to that transition, which is higher in energy. But then we get this intermediate product, which is a carbocation. It's not what you would consider stable, but it's stable enough where we can isolate it under really cold conditions. Or we can capture it with a competing product. And in this case, we have our second reaction, which I usually just do with arrow pushing. And this gives us our product. Call this our product. But once again, this transition state is just this bond forming. So as we're looking at reaction coordinate diagrams in the future, there's going to be a lot more stuff like this than what you're used to seeing, which is kind of your more simple versions that look like that. And when we get into Biochem 1, which I'm sure everybody here is super excited about taking, when we're dealing with enzymes, it gets significantly more complex in how we view these. So we're going to start adding more complexity to coordinate diagrams. Now notice that I intentionally have a nice well here, and that the second transition state is lower than the first transition state. Because if it wasn't, it would likely push it back the other direction first. because of kinetic favorability of the reverse reaction being settled. So there's some rationale that we'll use in this to help explain reactions in the future. But that's it for chapter 5. Chapter 6 is going to be like this, but more. So this would be a really good time to bust out the note cards. Does everybody remember? Not that there's, okay, I don't want to downplay it. There's plenty of reactions in chapter 6. Push electrons. Get out a piece of paper and a pencil. Do the mechanisms. As you're doing the mechanism, explain it to yourself. What's the rationale for each step? I had a former student who's an anesthesiologist now who actually, and she was a single mom. I think she had her son when she was 17. And so as he was going to bed, she was trying to study organic chemistry. Nothing puts anybody to sleep like organic chemistry. So she started making up these children's stories where, which you'd have all these different reactions. And so it was like, for classic nucleophilic attack, you'd have this friend that had an abundance of something, and then you have this other friend who, didn't have much, and then there was this time where they were kind of sharing, but they hadn't really handed off. I don't know. I don't know how the actual story went, but I know that I got her in a lot of trouble by relating that story in a letter of reference. And then on the spot, one of the people interviewing her demanded that she tell them one of these stories that they were so impressed by. And she had no idea, like, in years. Since she'd had OChem even. And she did okay, I guess, because they accepted her. But whatever helps you rationalize these, go through the rationale like you're explaining it to somebody third party. And I really recommend the note cards. Remember, 2 ways. You've got on one side of the note card, we've got some nucleophile plus some electrophile lead to question mark, and then you flip the thing over and it's your product on the other side. And then you have the question, with reaction conditions X driving the reaction. And then let's say we've got some reaction and we want to go A plus B goes to product P. And the question is, how do you make this happen? And you have to flip the card over and say what the reaction conditions are. Because both processes, if you practice only one way, you're going to really struggle with synthesis. If you only struggle with synthesis, you're going to have a hard time discretely recognizing products. Just make note cards 2 ways for every reaction. Keep them separate from each other so you can drill them independently. And just stay on top of the reactions as we start to get it. Yeah?
These are all technically 2-way arrows, right? The reaction.
It depends. I mean, technically, reactions are to some degree reversible, but there's a threshold where a single-sided arrow is okay. Most of our reactions will be equilibrium style reactions, but there will be exceptions. And that's it. I'll see everybody on Wednesday, starting chapter 6.